Okay, we're going to pick up where we left off with half-life and the exponential growth and decay. And here's our first problem, problem number 6. Scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei already present have decayed. Originally present. I do want to point out that there's at least one homework problem where they expect you to know that carbon-14's half-life is 5,700 from having done this problem. So maybe just make a note of that, because I had to look it up. I was like, well, where's the number that I need? And in the solution, it said you were supposed to know it was 5,700 from the example problem. Anyway, okay. So I'm going to set up my generic exponential equation, and I'm going to list the points 0, 100, and 5,750. So 0 and 5,700 represent the time, and 150 represent the amount of carbon that's left. Now, I made up the hundreds, the numbers 150, but I like to put those numbers in there. They help me. So the important part is that this number be half of this number. It doesn't actually matter what it is. So when we divide both sides by 100, we're going to get 1/2 equals e to the 5,700k. Solving for k, I'll have to take the natural log of both sides, giving me ln 1/2 equals 5,700k, and then ln 1/2 over 5,700 equals k. Now that's going to be some gross number, and I don't really care what it is. So I'm just going to use that number and plug it in my formula. I'm going to leave y0 blank because I don't actually know what it is. I was just pretending it was 100. ln 0.5 over 5,700 times t. So this is our generic equation for this particular carbon-14. Oh my goodness. For my generic carbon-14 problem here. Now the question is, find the age of a sample where 10% has decayed. So if 10% has decayed, then there's 90% left. So if I started with 100, I'd be left with 90. And they're asking how long is that going to take. So I'm going to divide by 100 and get 0.9. I'm going to have ln of 0.5 over 5,700 times t. My variable is in the exponent, so I'm going to natural log both sides. This is really also times ln e, but ln e is 1. So t is going to be 5,700 times ln of 0.9 divided by ln of 0.5. And that's going to be 866. So that means that this sample in which 10% of it has decayed is approximately 866 years old. Okay. All right, so there we go. No calculus, really, just a whole lot of algebra. Okay, the next kind of problem that we're going to talk about is Newton's law of cooling. Okay, Newton's law of cooling can be described with the differential equation dt dt equals negative k times t minus t sub s. There's a lot of variables here, so let's talk about what they mean over here. Little t is time. It's often in minutes, but I don't believe that it really matters as long as everybody's in the same unit. Capital T is the temperature after some time has occurred. So maybe we'll say final temperature. TS is surrounding temperature. So that might be room temperature or the temperature of whatever is around that the substance that's cooling is in. And here's K again. That's our generic constant. The other number that is going to come up, the other variable rather, is T0. And that is the original temperature of, I guess we'll just say the sample. Okay, a lot of variables, I know. Okay, so Newton's law of cooling has this differential equation. And we can certainly work backwards to get the actual equation that is Newton's law of cooling. It's a little cumbersome, though, and I'm just not really sure you really want to know it. If you really are desperate, I'll just post my notes, and then you can see me do the calculus in there. But it's really kind of strange, so I'm just going to skip those steps. So we wind up with T0 minus Ts times e to the negative kt equals T minus Ts. Okay. See, it's kind of a nasty formula. Okay, I had left a lot of space here because originally I was going to do that calculus, but I gotta tell you, I just really don't think it's worth it. Okay, so here's an example. A hard-boiled egg at 98 degrees Celsius is put in a pan under running water that's 18 degrees Celsius. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees Celsius? Look at all those temperatures. That's crazy. Okay, so 98, that's TO, because that's the original temperature of the egg. 18 is TS, because that's the surrounding temperature. That's the temperature of the water that you're going to put the egg in so that it stops cooking. 5 is a time, so that's a little t. And after that, 5 minutes has gone, the temperature is found to be 38. Oh, that's kind of tricky, because what is 38? Is 38 T? I guess so. I guess that's final T. How much longer will it take the egg to reach 20? Okay, so this last sentence, that's for later. We're not dealing with that right this minute. So imagine that this was Algebra 1 or Algebra 2, and I gave you 2 points, and I said that the relationship between them was linear, and that you were going to, write the equation of a line and then use that line to predict some other, thing down the future. That's really what's going on here. It's just that it's not a line. Okay, so I'm going to set up my Newton's law of cooling formula. So that's TO minus TS times e to the negative kt equals T minus TS. So the one thing that we don't know here is K. Just like if we were to write a line, we wouldn't know the slope until we went and found it. Okay, so T0 is 98. And TS is 18. E to the K times, 5 minutes went by, And then the temperature of the egg was 38. And TS is still 18. Okay, so far? All right, let's simplify this a little bit because this is kind of a mess. So we're going to get 80 e to the negative 5k equals 20. And now we can just use some algebra and solve for k. E to the negative 5k equals 20 over 80, or 1/4. Take the ln of both sides. Oh, let me do that up here. I'll write ln. So negative 5k equals ln of 1/4. So k equals ln of 1/4 over negative 5. Again, that's going to be some gross number. Okay. That could be simplified. I mean, that does equal ln 4 over 5. It doesn't matter at all, but I don't know, just throwing it out there. Okay, so now we're going to write our real equation that has k in it for Newton's law of cooling for this particular problem of the egg. Okay, so that's going to be T minus TS, right, equals TO minus TS times e to the negative KT. That's like I'm saying y equals mx plus b or something. Okay. Now the final temperature now I want to be 20. So I'm actually just going to leave that alone. So T minus 18 equals 98 minus 18 times e to the negative ln 4 over 5 t. So I can simplify that a little bit. I can say t equals, I can add the 18 to the other side, put the 98 and the 18 together and get 80 e to the negative ln 4 over 5. Okay, so now this is my equation, and now I could put in anything I want for t time or t temperature, and I could find the other one. So this is where I'm going to put in 20 for c, 20 for t, sorry, and work backwards to find the time that has passed. I'm going to subtract 18 and get 2 equals 80 e to the negative ln 4 over 5t. I'm going to divide by 80 and get 1/40. I'm going to natural log both sides. And then I'm going to solve for t. And that is 13.3. Now, I want to point out that and I've seen this on an AP question, so I really want you to pay attention. T, 13.3 minutes, that's from the beginning. So that's not after the initial 5 minutes, but that's before that 5 minutes has even happened. So I want you to notice that the question says, how much longer will it take to reach 20 degrees? So 5 minutes have already passed. So how much longer? 8.3 minutes. More. I should put that. 8.3 more minutes. And that is the end of exponential growth and decay. I hope you've enjoyed this video. Make sure to subscribe and give me a like. Totally kidding. Totally kidding. I love you all. See you tomorrow.